I'm very happy to be here. Thanks to the organizers for this opportunity. Happy to be here. My name is Panous, coming from University of Chicago, and I will talk about sample bias in machine learning and what we can do about it. Before I start, I should apologize. Sometimes you'll see me looking the other way. I have a bigger screen there. The screen of my laptop is broken, so I have the camera on one side and the monitor on the other side. So apologies for that. Okay, so let's begin. So we know that statistics and machine learning models, they do work in a fixed sample. Okay, so but you know, we work in a fixed sample, but what we want to learn is something about the superpopulation. And so the common assumption in order to make that connection is that the data are randomly sampled from a superpopulation. Most commonly, we assume that the data are IID. Now, when this condition does not hold, which should be almost always the case, we have sample bias, and that sample bias can lead us to make mistakes, make wrong decisions, and so on and so forth. So it potentially can be a big issue. Now, that's not such a groundbreaking concept, right? Sample bias is well known, but there's no systematic way of dealing with this, right? All these methods that we have to assess uncertainty, asymptotics, bootstrap, cross-validation, all of them work in the sample, and more or less they just ignore the sample bias. So at best, we employ heuristics in practice, and we don't have something specific to work with. So today, I'd like to talk about some ways of dealing with that issue. My first argument is that, in general, it's impossible to address the issue with full generality, but there is something we can do about it. Okay, we can be optimistic and ambitious and perhaps try to address simpler questions. And today, I will try to address the detection of sample bias, which is an easier question than just trying to address the bias completely. So, just to spare you all the setup and the formulas, I'll just use my drawing skills to make the the setup here, and hopefully help motivate the issue. So generally, what we assume is that we have this superpopulation here. I'll just use that tilde for that superpopulation, which is generally unobserved. Okay. So the model that I'm going to consider here is the superpopulation where after that, there is what we call selection, okay? And that selection, it can be represented by a binary variable. I would call it Ri. And so when this binary variable is equal to 1, we get to observe that data points. So now it becomes Yixi, our familiar terminology. And then when this Ri is equal to 0, then we just drop this data point I, okay? So it's important to remember now that all this data that we observe, all of this is happening after selection, after the data point has been selected into our sample, okay? So this is where we do stats and machine learning. And it's always a good idea to remember that everything here, everything we do in practice is conditional on that selection being equal to 1, okay? So in the superpopulation, we have perhaps the superpopulation model, let's say regression model of Y given X. And that can be anything. It can be your regression, it can be a tree, it can be a deep net, and so on and so forth, a stats or a machine learning model. Whereas here, what we're doing is this conditional probability, this regression model, but it's also conditional on the sample, or R equals to 1. So whatever we do, whatever procedure we do, it has to be conditional on this R equals to 1. However, we're also interested to know how these two things connect, okay? Whatever we find in the sample, does it really translate to something real in the population, okay? So this is basically the talk today, trying to make that connection. So if you we can write down a little bit of formulas to try to understand where the issues come in, like why can we not make that connection immediately? Well, this is again, that's a population model, and this is what we learn in the sample, okay? So the problem is that the population model is some combination of what is in the sample and what is in the selection mechanism, as we say, okay? Let me call this the selection mechanism. And you see that the selection mechanism enters in many places. Is one over here, and we also have the model in the data that were not selected. Okay, so there are terms here that I know. For instance, that model over here is something that I know I can observe and I can try to fit and model. But there are other terms here that are fundamentally unknowable, right? For instance, that term over here, this model is unknowable. I cannot learn it because I don't get to see this data, so I cannot get to fit my model. However, all of these terms enter into the population model. So it is possible that whatever I learned in the sample, like with this model, this regression model, let's say, and I'm going to use phi hat to just denote the model that you learn. So it is possible that this model that you learn is not really connected very well to the population model, right? Just because of that equation over here. And so the question is, in general, we cannot recover the population model, right? Because we have so many unknowns, but can we do something about it? Let's start with some known concepts, which, even though they're not going to be very useful to us, it might help us connect to related work. The first one is the idea of an ignorable mechanism, okay? And that's an idea developed by Rubin in the 70s and others. So ignorable mechanism is basically a mechanism that selects based on observables. Like the outcomes, for instance, do not matter, as you can see over here. We can drop this Y. So these data are selected not based on the outcomes, but they only based on something that I can observe. Okay, that's an ignorable mechanism. And why this is good? It's good because if you happen to know this quantity here, that probability of selection given the observables, then whatever inference you do conditional on selection, it's fine for unconditional. It's fine unconditionally, and that's basically the same intuition in causal inference when you do propensity scores and so on and so forth. Again, it's not something really groundbreaking. However, the problem is that this too almost always never works, right? We never know it even. We also don't know this probability of selection given the observables in general. Even though in causal inference, we can learn it, right? Because we do observe, let's say, treated and controlled units. Here, like we do observe 1 and 0 cases. Here, we only observe the 1 cases. All the other cases that correspond to the 0, like R being 0, are not observed. So that's fundamentally unknowable. So we cannot test 2. We don't know this probability even when 2 holds. And in general, there's another issue here that if you take the space of ignorable mechanisms and the space of non-ignorable mechanisms, you can find 2 mechanisms that are arbitrarily close to each other. So as a concept, it's not as clean, right? It's not as rigorous. So it's more like a practical concept rather than something mathematically too rigorous. Okay, so just I'm being abstract here. So let me give you a concrete numerical example just to ground these concepts. And that's a calculation you can do in your computer. It's super easy, and you can see where the problem, what the problem is. So suppose we have in the superpopulation we have xi, like we sample this covariates as standard normals. We have a logistic regression model where we make sure that in this logistic regression model there's no connection between x and y. Okay, so no effect on x and y at all. Okay, simple logistic regression model, just univariate. And I set up a selection mechanism, this R binary variable, as being non-ignorable. And I'm using this complicated formula. It's not as hard as it looks. So roughly speaking, we're only going to select these data points where y is equal to 1 and the x is going to be small, and y is equal to 0 and the x is going to be large. Okay, so artificially, I'm going to introduce this bias such that when you run your regression model in the observed data, then you can see that you get a coefficient here that's minus 0.4. It's negative and strongly so. Okay, so then the model is very confident that this coefficient is very strong, and that's the problem of sample bias, right? You can see that here the effect is completely due to the sample bias. Originally, you see there was no connection between outcomes and variables. Here, all this non-ignorable vacuum, this selection bias is introducing that bias in my coefficient. Okay, and you can see the model is also very confident about it, and that's potentially a very big issue, right? Suppose this outcome is something, like something like social, some social policy, and then this X is something protected or like sensitive attribute. Like race, ethnicity, and so on and so forth. So the problem here is that you run your model in the sample, you find something, some effect, you think it's very strong, but you go back into the superpopulation that doesn't hold at all, right? So it leads to mistakes in inference, it leads to mistakes in decisions. And as I said, you try some methods like cross-validation, Bootstrap, that hopefully try to give you better sense of the uncertainty. They don't work. right? Because everything works in the sample. They just perpetuate all the bias that there is in your sample, just keep perpetuating in that resampling that they're doing. There are also multiple imputation methods that, generally speaking, cannot help also because they focus on marginalizing over the uncertainty of missing data. And so they generally don't address sampling bias issues. But potentially they could be refactored, potentially they could be used, but in general, that has not been their primary goal. Now, I have like sitting on that cross point here, I have some bad news and some good news. My argument here, and this is the bad news, is that generally there's nothing we can do about this, right? Because that selection probability can depend on the data in an arbitrary way, right? It can be, and even the model that in the data that you don't see can be arbitrary. Now, you could say, okay, let's impose some conditions, some assumptions, continuity, blah, blah, blah. But then very quickly it becomes speculative, right? Because you just don't get to observe a lot of your data points. So it can become speculative. What I prefer, what's closer to my tastes, is to try to solve simpler questions, right? If you cannot address this bigger question, what is a simpler question we can ask and address here? And I have identified two here. There may be more. So the first one is a detection problem. Can we really detect whether there's a sampling bias altogether? Okay, if I cannot debias things, if I cannot address it, can I even detect if we have a sample bias problem at all? And the second question is, can we test whether the effects that we find with our stats ML model is really, could it be completely driven by sample bias? But there's no relationship in the superpopulation. So these two questions, they might appear to be strict, but I argue that they're useful in practice. So let's see how we can address these two questions. And surprisingly, we can address them with very few assumptions. So we can be quite robust as well. Okay, so if there are any questions, please feel free to stop me or kind of ask me. I just see some questions in the chat. I'll just take a quick. There's a question about why do we think bootstrapping will not help reduce the bias? The problem is that bootstrapping works conditionally or on the selected data. So when you do resampling, you just keep resampling your observed data. And if there's bias in the observed data, there's nothing you can do about it, right? It's just, you keep perpetuating in these resamples, you keep perpetuating the data, the bias in the observed samples, okay? And another way to say this is that for Bootstrap to work, you need the assumption that your data come independently from a superpopulation. That's why, you know, when you do this resampling, the idea is that you are reconstructing the superpopulation distribution of your data. So it's a pretty bold claim, and in almost all cases it's the wrong claim. Just put simply. Okay, so great question though. Okay, so let me try to address these two questions now. Can we detect whether there is sample bias? Two, could the effect that we find in the data be purely due, mainly due, mostly due to the selection bias, the sample bias? Okay, question number one. Now, in this question, I'm going to assume that we know the distribution of my x's, my covariates, my features in the superpopulation. Okay, it's not a particularly crazy assumption, right? In the population, we do know, for instance, the distribution of age, the distribution of race, ethnicity, and so on and so forth. We do have marginal descriptions of these distributions. So what do we do? Well, fit your stats ML model. Let's call this phi hat on the selected data. Okay, so and you do any model that you want. You can do regression, you can do trees, you can do deep nets. Completely fine. You do you. So you feed the model, and then you take these f hats. These are your predictions in the sample, and then just because you know the superpopulation, you can take this f hat model that you learned and then apply it on the superpopulation. Okay, so now you have a distribution for the superpopulation values and then for the sample, and then you only test whether these distributions are equal. And you can do a KS test, you can do independence test, you can do many different things. So that's not particularly groundbreaking, I should say. And I'm sure some version of this exists in practice, but it's good to write it down, I guess. So So we test that, that hypothesis, and though if we reject it, then we know that the data are not a random sample from the superpopulation. So we know that there may be an issue with our inference. Now, I should say that this could be done immediately just by looking at the x's. We don't even have to look into the y's. We don't even have to fit a model. We just look into the x's, the features, and we test whether they match the superpopulation. But hopefully this ML model that we're using is a sharper way of testing that. Now, the practical problem here is that this P0 might be hard to know. In practice, we might not know it. Or if my x's are high dimensional, it might be a multi-dimensional distribution, and then it might be like really hard to know what it is. But here's how this works in practice. It's very simple. As I said in the previous example, where I saw the simulation where I biased the inference. I can fit the model. I have these phi hats from the logistic regression that I fit, and then I know the population distribution because it's simulation, and then I put them together, and then I test whether this match, and they don't match, right? So this test is able to figure out that there's something fishy that happened in this selection. Okay. All right. That's not too surprising, though. Let's go to method 2, which I think is more interesting and more tricky. In this case, I'm not going to assume there's a superpopulation, that we know the superpopulation distribution. And it might seem weird, like, what can you do? You don't know the selection mechanism. You don't know the superpopulation. What on earth can you do in this case? And the big problem is that you cannot disentangle the selection with the model, like the R model with the Y model. Okay, if you remember that equation in the superpopulation, it's a bundle. It's an interaction between the selection mechanism and the Y model. So this seems hopeless, but it also suggests an idea, right? It suggests that perhaps we can test both. So here's one null that we can test actually, which even though it might appear strict, I think it's quite interesting. So what we're going to test is the following: like this phi hat, the model that the kind of model that your machine learning method learns. We're going to test whether this is completely due to the sampling mechanism, to the sample bias. And at the same time, there's no connection, there's no relationship between your Y's and the X's. So whatever you find in the data, we're going to test whether this is due purely to a sample bias. Okay. And as you can see here, this is a joint hypothesis between the selection mechanism and the Y model and the Y mechanism. And necessarily so, because these two things come bundled together. Now, this is a strict hypothesis, right? But I still argue this is useful, okay? And let me show you an example. Before the example, let me show you how we can test that, and then we can get back into the example. So this is a hypothesis that we want to learn. Basically, we're asking, again, intuitively, we're asking, is what we learn entirely due to sample bias? So sorry, let me pause really quick. There's a question: is it possible to generate sample data using synthetic data generation algorithms to have unique representations of superpopulation of data to train model? It is possible. So I think the idea here is, can I try to just generate data, and so I have samples from R0 and R1? That's possible, but I guess this relates to my comment of, then we're kind of getting a little bit more speculative, right? We're kind of imposing assumptions. We're imposing modeling assumptions. So perhaps it gets too speculative, but it's definitely a good idea. Another question: if the learned model is partially driven instead of completely driven by sampling, will that be a problem? That will be a problem, and I think that's something we cannot test, because when we say it's partially driven, then the question is how much partially, right? It can be it's a very big set of possibilities after that, so it cannot be tested. That's why if you want to be model free, you have to test this type of sharp hypothesis. That's why I said it's a strict hypothesis, but at least we can test it in a kind of non-parametric way, right? Like in a model-free way. Okay, I need to wrap up. Under the null hypothesis, the main implication is that the data conditional on selection and conditional on the fitted values from your ML model are the Y and the X are independent. So what can you do? Very simple. You fit a stats model. You take this phi hat, these predictions. You bucket your data according to those predictions, and then within every bucket, you test for independence between the Y and X's. That's it. Okay. So all the tools, the parts are there. It's a combination that perhaps is novel here. And here's how it works in this case. In the previous case where I had this artificial selection, this controlled sample bias. If you do this trick, you have this is the p-value of independence for every for every bucket, you'll see that the minimum p-value is 0.02. If you correct it for multiple testing, it becomes 0.2. So you cannot reject it here. What does this mean? It means that in this previous model where I had, remember this logistic regression model, no effect, but with a non-ignorable selection, you see that we cannot reject this null. So basically, it could be the case, the data do not reject this hypothesis that whatever we find, this minus 0.4, this very strong negative effect, we cannot reject that it's entirely driven by the selection bias, which I think it's a cool result. There are some implementation issues that I don't want to get to. It's more like trivia. I should say though, like, why do I talk about stats and machine learning? I talk about stats and machine learning because these models are very flexible, and they can learn these five hats in a very flexible, very aggressive way. And that can be this is a peril, I think, of machine learning. This is the danger with machine learning methods. They're very aggressive, they're very powerful, and what they might be learning, they might not be learning the relationship between y and x. They might be learning the selection mechanism. And that's an important issue that's completely forgotten. And I think, and actually we found it to be an issue in other applications as well, completely unrelated, but still a real issue. So that's why I talk about ML, because it can be very aggressive in learning these 5 hats. And then you go back, you look at the 5 hats and you say, oh, I found something, but you might be learning the sample selection mechanism. Okay, my time is up. So I will just say that there is an application where I looked into math performance, and there's a sex variable there that's recorded as binary. And I should say that I ran this test, and even though in the sample you see there's a very strong effect from being male that it kind of increases the math performance, you run this test and you find that this positive effect could be spurious. Now, it cannot reject the hypothesis that it could only be that this effect is coming from the sample bias completely. And that's reasonable here because the data come from only one school in Portugal. So is reasonable to that you have issues of sample bias. And I do some calibration study where I control things, and this test is not only, it can reject in many cases when it should reject in a calibration study. Okay, that's all. I should just kind of wrap up by saying that, again, be careful about machine learning models. They're very powerful, but what you learn, it might be the sample bias and not the actual effect. And that's, I described just one way to test that. So thank you so much for your attention.